Hey there, cosmic travelers. Welcome back to the channel. Or if you're new here, welcome to the family. Look, I know you've probably heard the phrase, the universe is big, 1,000,000 times. It's almost a cliche, right? We throw it around when we're trying to make a point about something being huge. But today, we're not just going to say it. We're going to feel it. We're going to wrap our minds around the single most mind-boggling, humbling, and awe-inspiring fact we know, the sheer, staggering size of everything we can possibly see. We are going to answer, in the most detailed way possible, the question, how big is the observable universe? Before we launch into the infinite, if this is the kind of journey that blows your mind and makes you stare at the ceiling at night, do us a huge favor. Hit that like button. It tells the algorithm that this is worth sharing with other curious minds. And if you haven't already, please subscribe. We dive deep into the wonders of reality every week, and we'd love for you to be here for all of it. And here's a fun thing. Drop a comment down below and tell me where you're watching from and what time it is for you. Are you having a late-night cosmic contemplation session? A lunch break adventure? It's always amazing to see our little community of stargazers spread across the globe and across the clock. Okay, with that out of the way, fasten your seatbelt. We have a lot of ground, or rather, a lot of space, to cover. First, let's get our terms straight. What do we even mean by the observable universe? It sounds simple, but this is the most important concept we'll talk about. It's not the whole universe. It's not everything that exists. The observable universe is a very specific, and frankly, a very personal thing. It is, quite literally, your universe. It is the giant, spherical bubble of space centered on you, yes, you, right where you're sitting, that contains all the matter and energy from which light, or any other signal, has had enough time to reach you since the beginning of everything. Think of it like this. Imagine you're standing in the middle of a vast, foggy field at night. You have a flashlight. The beam of your flashlight can only illuminate so far. Everything within that circle of light is observable to you. You can see the trees, the grass, maybe a few animals. But beyond that beam? There could be mountains, oceans, entire cities. But you have no way of knowing, because their light hasn't reached your eyes yet. The observable universe is that circle of light for the entire cosmos. The flashlight is the Big Bang, and the fog is the 13.8 billion years that have passed since then. The edge of what we can see isn't a physical wall, it's a horizon in time. It's the ultimate. You had to be there event, and we're seeing the echoes of it that have finally arrived at our doorstep. So, the first key ingredient in sizing up our cosmic bubble is the universe's age. Thanks to incredibly precise measurements of the cosmic microwave background, the faint afterglow of the Big Bang itself, we know the universe is about 13.787 billion years old, give or take 20 million years. That's our starting stopwatch. Now you might think, okay, if the universe is 13.8 billion years old, and light is the fastest thing there is, then the farthest thing we could possibly see should be 13.8 billion light-years away. That seems logical, right? A light-year is the distance light travels in 1 year. So, in 13.8 billion years, light should have traveled 13.8 billion light-years. That would give us an observable universe with a radius of 13.8 billion light-years and a diameter of 27.6 billion light-years. But you'd be wrong. And this is where things get wonderfully, beautifully weird. The actual radius of the observable universe is not 13.8 billion light-years. It's about 46.5 billion light-years. The diameter is about 93 billion light-years. Wait, what? How can we see something that's 46 billion light-years away if the light has only had 13.8 billion years to travel? That seems like a cosmic cheat code. Did something break? No, nothing broke. The universe just decided to play a trick on us called expansion. And this isn't a small detail, it's the reason our cosmic home is so unimaginably large. The universe isn't static. It's not like a frozen sculpture where galaxies are pinned in place. Space itself, the very fabric of reality, is stretching. It has been stretching since the first moment of the Big Bang. This means that the galaxy that emitted a photon of light 13 billion years ago wasn't sitting still, waiting for its light to reach us. It was, and still is, racing away from us because the space between us and it is growing. So, by the time that photon finally completes its marathon journey across the cosmos and hits the lens of the James Webb Space Telescope, the galaxy that sent it is much, much farther away than it was when the journey began. The light tells us where the galaxy was, but the expansion of space has moved the finish line. Let's try a simpler analogy. Imagine you're on a moving walkway at an airport, and you throw a ball to a friend standing at the other end. The ball represents light. The moving walkway represents the expanding universe, slowly carrying your friend away from you. By the time the ball reaches where your friend was when you threw it, the walkway has carried them farther back. So, the ball had to travel a longer effective distance than the initial static distance between you. That's what's happening across the entire universe, but on a scale so vast it's hard to comprehend. This expansion is described by Hubble's law, named after the astronomer Edwin Hubble. In the 1920s, he made the groundbreaking discovery that almost every galaxy we look at is moving away from us, and the farther away it is, the faster it's receding. This wasn't because we're at the center of some cosmic explosion, we're not, but because space itself is expanding everywhere at once. Picture a raisin cake baking in the oven. As the dough rises, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are receding. That's our universe. We're just one raisin in an infinite, or nearly infinite cake. Now, if you just hear that, your first, perfectly reasonable human thought might be, "Yikes! Did we do something to offend the cosmos? Are we at the center of some giant galactic explosion?" It feels that way, doesn't it? It feels like we're the unpopular kid at the dance and everyone is backing away. But the truth is so much cooler and so much more humbling. We are not the center. There is no center. Not in the way we think of one. The magic, the absolute showstopper, is that space itself, the very fabric of the nothing, between the stars, is stretching. Growing. Expanding. Everywhere, all at once. Imagine that raisin cake dough again, but now let's really zoom in. You are one raisin. I am another raisin. We're sitting in this dough. Now the oven is on, and the dough begins to rise. It doesn't expand from one point outward. The entire loaf, every single cubic inch of it, puffs up uniformly. So, let's say the distance between you and me was 1 inch. After the dough doubles in size, that distance becomes 2 inches. Now, look at a raisin that was 2 inches away from you to start. When the dough doubles, that distance becomes 4 inches. From your perspective, that farther raisin didn't just move 1 inch farther, like I did. It moved 2 inches farther. It appears to have receded from you at twice the speed I did, even though the dough itself just expanded at the same rate everywhere. That is our universe. Every galaxy is a raisin. The expanding space-time is the dough. From every single raisin's point of view, all the other raisins are moving away. And the ones that started farther away appear to move away faster, simply because there's more expanding dough between you and them. There is no privileged spot. If you could instantly teleport to a galaxy 10 billion light-years away in another part of the cake, you would look around and see the exact same thing. Every other galaxy speeding away from you, with the most distant ones fleeing the fastest. It's a cosmic democracy of recession. This is the heart of Hubble's law, and it utterly transformed our understanding from a static, unchanging universe to a dynamic, growing, evolving entity. Now, how on Earth, or rather, how from Earth, did Edwin Hubble figure this out? He didn't have a cosmic speed gun. He couldn't watch a galaxy move in real time. His evidence came from starlight, and a very special trick that light plays when its source is moving. It's called the Doppler effect. You hear it all the time. When an ambulance races toward you, its siren sound waves get compressed, making the pitch higher. As it zooms away, the waves get stretched out, making the pitch lower. Light waves behave in a nearly identical way. When a source of light is moving away from us, the waves get stretched. Since longer wavelengths of visible light are redder, we call this phenomenon redshift. In the early 1900s, an astronomer named Vesto Slipher was looking at the spectra, the chemical fingerprints, of these fuzzy spiral nebulae. He found that the fingerprints of elements like hydrogen and helium in their light were almost always shifted toward the red end of the spectrum. They were, almost universally, racing away from us. This was the first big clue. But Slipher didn't know how far away these nebulae were. Were they nearby objects in our Milky Way, or were they island universes far beyond? That was the great debate. Enter Edwin Hubble. Working with the powerful 100-inch Hooker telescope at Mount Wilson Observatory, he was able to resolve individual stars within some of these nebulae, particularly in the Andromeda Nebula. Among those stars, he found the key, Cepheid variable stars. These are cosmic lighthouses with a brilliant property discovered by Henrietta Swan Leavitt. Their intrinsic brightness is linked to the rhythm of their pulsations. A Cepheid that pulses with a certain period is always, anywhere in the universe, the same true brightness. By comparing how bright it truly is to how dim it appears in his telescope, Hubble could calculate its distance with unprecedented accuracy. And the answer was staggering. Andromeda was millions of light-years away. It was not part of our galaxy. It was an entirely separate galaxy. The universe had just gotten unimaginably larger. Hubble now had a toolkit. For a growing number of galaxies, he, and others like Milton Humason, had a redshift measurement from Slipher's work, telling him the velocity. And he had his Cepheid measurements, giving him the distance. He began to plot them. On one axis of his graph, he put distance. On the other, he put recessional velocity. What he saw, despite some scatter, was a revelation. The points didn't form a random cloud. They lined up. More importantly, they lined up in a straight line that went through the origin. Zero distance meant zero velocity, for the expansion, anyway. Double the distance meant double the velocity. Triple the distance, triple the velocity. It was a clean, linear, proportional relationship. This was the birth of the Hubble diagram and the formal statement of Hubble's law, which we write as a beautifully simple, world-changing equation, V is equal to h0 multiplied by d. In that equation, V is the galaxy's recessional velocity. D is its distance from us. And h0? That's the star of our next act. That's the Hubble constant. It is the slope of that line on Hubble's graph. It is the number that tells us exactly how much faster a galaxy recedes for every single unit of distance you add. It is, in essence, the current expansion rate of our universe. It answers the question: how fast is the cosmic dough rising right now? Now, the unit of this constant sounds like jargon soup, kilometers per second per megaparsec. Let's dissolve that soup into something clear. A megaparsec, MPC, is a monster unit of distance. 1 parsec is about 3.26 light-years. A megaparsec is a million parsecs. So, 1 megaparsec is about 3.26 million light-years. It's the scale of distances between neighboring giant galaxies. So, what does 70 kilometers per second per megaparsec, a commonly used modern value, mean in the real world? It means that for every 3.26 million light-years a galaxy is from us, the expansion of space adds a recessional speed of about 70 kilometers per second. Let's make it concrete. A galaxy that is 10 megaparsec, about 32.6 million light-years, away isn't just drifting. The very space between us is stretching so that it appears to be moving away at roughly 10 multiplied by 70 equals to 700 kilometers per second. A galaxy 100 megaparsec away is receding at about 7,000 kilometers per second. A galaxy a billion parsecs away? It's moving at a significant fraction of the speed of light. This isn't because the galaxy itself is rocketing through space at that speed from its own engine. It's because there is a vast highway of expanding space between us and it, and every single megaparsec length segment of that highway is adding its own 70 km per second of stretch. Here's a crucial, brain-tickling detail. The Hubble constant is a bit of a misnomer. It is constant everywhere in space at a given moment. Every raisin in today's cake sees the same value of Hubble constant. But it is not constant in time. The expansion rate of the universe has changed dramatically over its 13.8 billion year history. In the frenzied first moments after the Big Bang, it was unimaginably fast during a period called inflation. For billions of years after, gravity from all the matter in the universe acted as a brake, slowing the expansion down. Then, about 5 billion years ago, something bizarre happened. The expansion started to speed up again. Something we call dark energy began to dominate, and push galaxies apart even faster. So, Hubble constant is a snapshot. It's the expansion rate of now. When we look at extremely distant galaxies, we are seeing them as they were billions of years ago, when the expansion rate, described by the broader Hubble parameter h/t, was different. This brings us to a fascinating modern mystery, the Hubble tension. You see, astronomers have two primary ways to measure Hubble constant. One is the local or late universe method, following directly in Hubble's footsteps. We use modern versions of standard candles, like Cepheids and the brilliant explosions of Type 1a supernovae, to measure distances to galaxies, and their redshifts to get velocities. This builds a modern, super-precise Hubble diagram. This method, championed by astronomers like Wendy Friedman, gives a value around 72 to 74 km per second per megaparsec. The other method is an early universe probe. We look at the cosmic microwave background CMB, the afterglow of the Big Bang from when the universe was only 380,000 years old. By exquisitely mapping the tiny temperature variations in this ancient light with satellites like Planck, we can deduce the universe's ingredients: ordinary matter, dark energy, and its geometry. Plugging all that into our equations of cosmic evolution tells us what the expansion rate should have been then, and thus what Hubble constant should be today. This method gives a value of about 67 to 68 km per second per megaparsec. These numbers don't agree. They differ by more than their respective error margins should allow. This is the Hubble tension. It's not a small squabble, it's a significant discrepancy that has cosmologists deeply excited and perplexed. It could mean there's a systematic error in one of our measurement techniques that we haven't found. But the thrilling possibility is that it might mean our standard model of cosmology, the lambda-cold dark matter model, lambda CDM, is incomplete. Maybe dark energy isn't as simple as Einstein's cosmological constant. Maybe there's a new type of neutrino, or some other exotic physics in play. The Hubble constant isn't just a number, it's a profound diagnostic tool for the health and history of our universe. Finally, let's connect this constant back to the mind-blowing size of the observable universe we talked about before. You'll remember I said that even though the universe is 13.8 billion years old, the radius of the part we can see is about 46.5 billion light-years. The Hubble constant is why this is possible. Those 46.5 billion light-years is the comoving distance, where the galaxy that emitted the light we see today is actually located now, after 13.8 billion years of relentless expansion. The Hubble constant quantifies that relentless expansion. Its reciprocal, 1 over h0, gives us the Hubble time. If the expansion had always been at today's rate, the Hubble time would be the age of the universe. With Hubble constant of 70 km per second per megaparsec, the Hubble time is about 14 billion years. It's remarkably close to the actual, more carefully calculated age of 13.8 billion years, But that's partly a coincidence given the history of slowing down and speeding up. This time, multiplied by the speed of light, gives a Hubble length, about 14 billion light-years. This is not the radius of the observable universe, but it is a key scale. The fact that the real observable universe radius is about 3.3 times larger than this simple Hubble length is a direct consequence of the fact that the expansion has accelerated due to dark energy. So, when you hold that Hubble's law in your mind, you're holding a key to the cosmos. It tells us the universe is dynamic. It gives us a speedometer for space itself. Its value is a bone of contention that might point to new physics. And it is the relentless engine that, over billions of years, stretched a once tiny, hot, dense universe into the vast, cool, galaxy-filled expanse we call home. Edwin Hubble's law didn't just discover galaxies were moving. It discovered that the stage upon which they sit, the fabric of reality, is alive, growing, and writing the greatest story ever told. So, we have our sphere. A sphere centered on Earth. And it is so big that the numbers, 46.5 billion light-years in radius, 93 billion across, just stop meaning anything to our brains. Our minds didn't evolve to handle this. They evolved to handle walking across a savanna, throwing a spear, maybe figuring out how far away that berry bush is. Not this. So, let's try to trick our brains into getting a tiny glimpse of it. First, let's shrink everything down to a scale we can almost hold in our hands. Imagine the entire observable universe, that 93 billion light-year wide behemoth, is shrunk down to the size of the Earth. Our entire planet is now the stand-in for everything we can possibly see. Got that image? On this scale, our entire Milky Way galaxy, that majestic spiral of 400 billion stars, 100,000 light-years across, would be about the size of a single grain of sand. One tiny speck. And our whole local group of galaxies, with Andromeda and a few dozen others? Maybe a small handful of sand. And that colossal sphere that is the Earth-sized universe? It would contain 2 trillion of those galaxy grains of sand. It's an amount of sand you could use to bury planets. That's the first hint of the sheer, raw volume we're talking about. Now let's step inside that volume. What's it like in there? The very first, most overwhelming truth is this: it is almost nothing. It is a void so deep, so complete, it makes the emptiest vacuum chamber we can ever build on Earth look as crowded and hectic as a city street. If you could take a magical cube, 1 meter tall, 1 meter wide, 1 meter deep, and place it anywhere at random in the intergalactic voids, the deepest, darkest spaces between the galaxy clusters, it would, on average, contain just a handful of atoms. Not molecules. Atoms. Lonely hydrogen atoms, drifting for millions of years without ever bumping into a neighbor. Scientists have a number for this profound emptiness: the average density of the universe. It's about 8.5 multiplied by 10 to power minus 27 kilograms per cubic meter. Let's break down that scary-looking number. A hydrogen atom, the simplest, most common thing out there, has a mass of about 1.67 multiplied by 10 to power minus 27 kilograms. So that average density is equal to about 5 hydrogen atoms per cubic meter. Yes, 5. In a space the size of a large refrigerator box. That's it. That's the average stuff of the cosmos. It is, for all practical purposes, nothing with a capital N. But if that's the average, and space is so empty, why is the night sky not just a perfect, uniform, black emptiness? Why do we see anything? Because of the most important word in that description, average. Matter is not spread out like a thin, perfect butter across the cosmic toast. It is lumpy. It is clumpy. It has, over 13.8 billion years, done the most spectacular and beautiful thing possible. It has gathered itself together against all the odds. This is the work of gravity. Gravity is the patient artist, the slow, relentless sculptor of the cosmos. It started with the tiniest of imperfections. In the first hot soup of the universe, there were quantum ripples, tiny spots that were ever so slightly denser than the spots next to them. Just a few more atoms in a region the size of a solar system. But gravity loves density. More mass means more pull. So those slightly denser patches had a tiny bit more gravitational pull than their surroundings. They started to gently tug on the atoms and dark matter around them. As they pulled in more stuff, they got denser. As they got denser, their pull got stronger. It's a runaway feedback loop that has been running for over 13 billion years. First, these patches pulled in gas, mostly hydrogen and helium. When these vast clouds of gas got dense and hot enough at their cores, crossing a threshold of about 15 million degrees Celsius, nuclear fusion ignited. A star is born. A single star is already a spectacular rebellion against the emptiness. It takes the diffuse matter of a huge volume of space and concentrates it into a brilliant, raging furnace. But gravity isn't satisfied with one star. Stars are born in giant groups from collapsing gas clouds, forming glittering star clusters. These clusters, along with billions of other stars, are then drawn together by their collective gravity into majestic, swirling structures, galaxies. A galaxy is gravity's masterpiece. It is a civilization of stars, often hundreds of billions strong, all orbiting a common center, bound together in a grand, slow dance. Our Milky Way is one of these. From a single grain of sand in our Earth-sized model, it becomes an island of light in the overwhelming dark. But wait, gravity's work isn't done. It looks at these galaxies and says, "You should have friends." Galaxies are social. They are almost never found alone. They gather into small groups, like our own local group. These groups then clump together into massive clusters, containing hundreds or even thousands of galaxies, all swimming in a superheated soup of gas that is so hot it glows in X-rays. These clusters are the largest gravitationally bound structures in the universe. And here's the final, mind-bending pattern: these clusters and groups are not scattered randomly. If you could take a God's eye view and map every galaxy in our colossal sphere, you would see a structure that looks like a sponge or a cosmic web. Imagine the universe is built like a loaf of the most intricate bread. The doughy parts of the bread, the soft, structured material, are the filaments and walls of the cosmic web. These are long, thread-like structures made of thousands of galaxies, stretching for hundreds of millions of light years. Where these filaments intersect, you find the dense, rich clusters of galaxies, the great knots in the net. And what's in the holes of the sponge? The bubbles in the cosmic bread? Those are the voids. Enormous, spherical regions of near total emptiness that can be 150 million light-years across or more. They are the true deserts of the universe, where galaxies are almost completely absent. This is where your 1-meter box would hold its 5 lonely atoms. The voids make up most of the volume of the universe, while the web of galaxies makes up most of its structure. So, when you look up at the night sky, you are seeing a profoundly misleading slice. The stars you see are in our own galactic neighborhood. The faint smudge of Andromeda is our nearest giant galactic neighbor. They feel close. They feel like the universe is quite populated. But that's an illusion of perspective, like standing in a small, well-lit town and thinking the whole world is just as bright and crowded. In reality, our town is a single speck of light on a single thread of a web that is mostly made of incomprehensibly vast, dark, and empty space. The overwhelming character of our cosmic sphere is a silent, freezing vacuum. But scattered within that vacuum, concentrated by the relentless, patient pull of gravity into islands of breathtaking beauty and violence, are the stars, the galaxies, the clusters, the glittering, rare jewels in the boundless dark. Let's start with the building blocks, galaxies. A galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and that mysterious stuff we call dark matter. Our home is the Milky Way, a beautiful barred spiral galaxy containing somewhere between 100 and 400 billion stars. For a long time, We had only a rough guess about how many galaxies were out there. But with deep field observations from telescopes like Hubble, which stared at a tiny, seemingly empty patch of sky for days to gather the faintest light from the most distant objects, we've been able to make better estimates. The current best estimate? The observable universe contains as many as 2 trillion galaxies. Let that number sink in. 2 trillion. That's a 2 followed by 12 zeros. Each of those galaxies is an island universe, containing billions or even trillions of stars of its own. Some are majestic spirals like our own, some are fuzzy ellipticals, some are irregular blobs. But each one is a city of stars. And the stars within them? That number is even more astronomical. The total number of stars in the observable universe is estimated to be around 10 to power 24. That's a 1 followed by 24 zeros, or about a septillion stars. It's often said that there are more stars in the observable universe than there are grains of sand on all the beaches and deserts of Earth. And that's probably an understatement. The sand grain estimate is roughly 7.5 multiplied by 10 to power 18 grains. We're talking about a number of stars that is 1,000,000 times greater than that. Now, if we tried to count the most basic building blocks of matter, atoms, the number becomes almost abstract. If we assume most of the ordinary, or baryonic, matter in the universe is hydrogen, scientists estimate there are about 10 to power 80 atoms in the observable universe. That's the Eddington number, a figure so large it's used as a benchmark for unimaginably huge in cosmology. Right, so we've established that our cosmic home is mostly a breathtaking, bone-chilling void. And yet, when we look deep enough, we find that the tiny sprinkling of matter out there isn't just tossed about randomly, like someone shook a salt shaker over the darkness. It's arranged. It's organized. On the very largest scales imaginable, the universe reveals a pattern so grand and intricate that it has a name, the cosmic web. Think of the universe like a vast sink full of soap bubbles, or a cosmic sponge. Most of the volume, the inside of the bubbles, is empty space. These are the cosmic voids. They are not completely empty, but they contain far less than 10% of the matter found elsewhere, making them the true deserts of the cosmos, some stretching for hundreds of millions of light years. Then, picture the soapy film that makes up the walls of those bubbles. That's where the action is. That film is made of galaxies. These vast, thin sheets and walls of galaxies can stretch for astonishing distances, like the Sloan Great Wall, which is nearly 1.4 billion light-years long. Where these soapy walls or sheets intersect, they form thick ridges. In our cosmic web, these are the filaments. These are the densest highways of the web, long, twisting tendrils of galaxies, gas, and dark matter. And where several of these filaments cross, you get the busiest intersections of all, the dense clusters and superclusters of thousands of galaxies, all swarming together in a chaotic, gravitationally bound dance. Our own Milky Way, for instance, lives in a modest galactic suburb. We're part of the local group, which is nestled on the outskirts of the Laniakea supercluster, itself just one part of a much larger filament. So, the picture is one of a three-dimensional spider's web, or a froth of bubbles. The luminous galaxies we see with our telescopes are like glitter glued onto the strands of this web. They trace out its shape, but they are not the main structure. The thread of the web itself is made of something invisible and far more abundant, dark matter. This mysterious substance, which interacts through gravity but not with light, makes up about 85% of all the matter in the universe. In the early cosmos, dark matter began to clump together first, forming an invisible skeleton. The ordinary atoms, the stuff of stars, planets, and us, simply followed this gravitational blueprint, flowing into the densest parts of the dark matter framework to form the galaxies we see lighting up the filaments today. Now, this leads us to the billion-year-old question: where did this magnificent web come from? How do you get such intricate, large-scale structure from what was, by all accounts, a hot, dense, and nearly perfectly smooth soup after the Big Bang? The answer is a story that starts in the most unimaginably brief moment of time and involves the two most powerful sculptors in the cosmos, inflation and gravity. Let's rewind the clock all the way back. Not to billions of years ago, but to a fraction of a second after the universe began. At this time, scientists believe the universe underwent a period of hyperaccelerated expansion called cosmic inflation. Space itself expanded faster than the speed of light, inflating a subatomic-sized patch of reality to something astronomically large in less than the blink of an eye. Why does this matter for our web? Because of what was happening on the quantum scale during this inflation. In the frantic quantum foam of that early moment, tiny fluctuations were inevitable. Particles and energy would pop in and out of existence, creating random differences in density. Some spots were ever so slightly denser, others ever so slightly less. Think of a perfectly smooth pond on an utterly windless day. Even it isn't perfectly smooth at the molecular level. Now, imagine that in a single instant, that pond was suddenly stretched to the size of an ocean. Those submicroscopic ripples would be stretched into giant, kilometers-long waves. Cosmic inflation did exactly that. It took those quantum fluctuations, those subatomic ripples in the fabric of reality, and stretched them to enormous, cosmic proportions. These stretched ripples became the seed, the template, for all future structure. The slightly denser patches were the future homes of galaxy clusters. The slightly less dense patches were the seeds of the great voids. For a long time after inflation, however, not much happened in terms of building structure. The universe was still too hot and dense. Ordinary matter, the protons, neutrons, and electrons that make up everything we see, was tightly coupled to light, or photons. Gravity would try to pull a slightly denser patch of matter together, but the intense pressure of the radiation would push it apart, like trying to clump together glitter in a blast of air. But dark matter, which doesn't interact with light, had no such problem. It was free to start clumping under its own gravity immediately. So, while the ordinary matter was stuck, the dark matter was quietly, invisibly, beginning to form the very first wispy tendrils of the cosmic web in the darkness. The next major milestone happened about 380,000 years after the Big Bang. The universe had expanded and cooled enough for a monumental change. Electrons could combine with protons to form neutral hydrogen atoms. This moment, called recombination, had two cosmic consequences. First, it freed the light. Photons, no longer constantly bumping into free electrons, could finally travel unimpeded. That released light, cooled over billions of years of expansion, is what we detect today as the cosmic microwave background, CMB, the afterglow of the Big Bang. If you look at a map of the CMB, you see a nearly uniform glow. But with incredibly sensitive instruments, we see tiny temperature variations, hot spots and cold spots. These are the direct, fossilized imprints of those stretched quantum seeds. The slightly denser regions from inflation appear as slightly cooler spots on the CMB map. The second consequence was that ordinary matter was finally set free from the pressure of radiation. Atoms, now neutral, could feel the gentle tug of gravity without being blown apart. And what were they drawn to? The invisible framework of dark matter that had already begun to form. Gravity, patient and relentless, took over. Over hundreds of millions of years, the slightly denser regions in the dark matter web pulled in more and more matter. They grew denser, which increased their gravity, which pulled in even more matter. This is a runaway process called gravitational instability. But gravity didn't pull things into simple, round blobs. The shape of the initial seeds and the flow of matter in 3 dimensions naturally led to a specific architecture. Matter didn't just fall inward from all sides equally. It flowed most easily along the paths of least resistance, streaming into the valleys and ridges of the gravitational landscape. Picture pancake batter being poured onto a griddle with a very subtle, wavy pattern. The batter will naturally flow into the dips, creating connected ridges. In a groundbreaking piece of work, astrophysicist Yakov Zeldovich described how this would form flattened pancakes of matter first. Where these pancakes intersected, you'd get dense lines, filaments. And where several filaments met, you'd get the densest knots, the future galaxy clusters. This is how the cosmic web emerged from the smooth early universe, not as scattered dots, but as a connected network of sheets, filaments, and nodes, with vast empty voids in between. The first stars and galaxies sparked to life in the densest knots of this web a few 100 million years after the Big Bang, ending the cosmic dark ages. These first-generation stars were behemoths, and their explosive deaths as supernovae polluted the pristine hydrogen and helium gas with heavier elements, enriching the cosmic web for future generations of smaller stars and planets. Over billions of years, the web became more pronounced. Galaxies formed along the filaments, drawn like beads on a string toward the giant clusters at the intersections. The voids, with their weaker gravity, expanded faster than the denser regions, becoming ever emptier and more distinct. Today, when we create massive 3D maps of the universe by measuring the positions and distances of millions of galaxies, we are essentially tracing the glitter on this dark matter web. The monumental structures we find, like the Sloan Great Wall, or the even more colossal Hercules, Corona Borealis Great Wall, which is thought to span a mind-numbing 10 billion light-years, are not single, bound objects. They are simply the most prominent overdensities in the web, the places where the filaments are most packed with galaxies. They are features of the web, not separate from it. The cosmic web isn't just a pretty picture, it's a living record and a powerful scientific tool. By studying its details, the thickness of filaments, the size and shapes of voids, the distribution of clusters, cosmologists can test our most fundamental theories of the universe. For example, the mysterious force causing the universe's expansion to accelerate, dark energy, has a stronger effect in the near-empty voids than in the dense clusters. By measuring how voids grow and change shape over cosmic time, missions like the upcoming Nancy Grace Roman Space Telescope hope to unravel the properties of dark energy itself. So, when you grasp the concept of the cosmic web, you are connecting two impossibly distant realms of reality. You are linking the frenetic, uncertain world of quantum mechanics in the first instant of time to the grand, majestic architecture of galaxies that we see today. The pattern in the glittering night sky is, in the most literal sense, a fossil. It is the blown-up, gravity-carved impression of the universe's quantum infancy, a permanent signature of its tumultuous birth written across the canvas of space and time. And how do we know all this? How can we possibly measure distances of billions of light-years or map this cosmic web? It all comes back to light. Astronomers are cosmic detectives, and light is their chief witness. But light can be tricky. As the universe expands, the light traveling through it gets stretched. This is the phenomenon of cosmological redshift. Just as the sound of a siren drops in pitch as it moves away from you, the Doppler effect, the light from a receding galaxy is stretched to longer, redder wavelengths. By measuring how much the light from a galaxy has been redshifted, astronomers can calculate how fast it's moving away from us. And using Hubble's law, they can then estimate its distance. For the very farthest objects, we rely on standard candles, objects whose intrinsic brightness we think we know. The most famous of these are a type of exploding star called a Type 1a supernova. Because these explosions have a very consistent peak brightness, we can compare how bright they look to us with how bright we know they are. The difference tells us their distance, much like judging how far away a car is at night by the apparent brightness of its headlights. These supernovae were key to the Nobel Prize-winning discovery in the late 1990s that the expansion of the universe is not slowing down, as everyone thought, but is actually accelerating, a finding attributed to the mysterious force we call dark energy. But the ultimate standard candle, or rather, the ultimate backdrop for all our measurements, is the cosmic microwave background, CMB. This is the oldest light we can see. About 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before this, the universe was a hot, dense fog of charged particles that constantly scattered light, making it opaque. When the atoms formed, the photons, light particles, were finally set free to travel unimpeded. That first flash of light, after cooling and stretching over 13.8 billion years of expansion, now reaches us as a faint microwave glow that permeates every direction in space. The CMB is not perfectly uniform. It has tiny temperature fluctuations, differences of about 1 part in 100,000. These tiny ripples are the seeds of all the structure we see today. The slightly denser patches had stronger gravity, pulling in more matter, eventually forming the galaxies and clusters we see. By studying the precise patterns of these fluctuations with satellites like COBE, WMAP, and Planck, cosmologists have been able to determine the age, composition, geometry, and expansion history of the universe with incredible precision. It's our baby picture of the cosmos. So, we've mapped our bubble. We know its size, its contents, and its history. But here's the final, and perhaps most haunting, twist. The observable universe is not a fixed thing. It's changing. Because the expansion of the universe is accelerating due to dark energy, there is a future visibility limit. There are galaxies whose light is only just starting its journey towards us today. But because space between us and them is stretching faster and faster, that light will never reach us. They are already over the cosmic horizon. Scientists calculate that the farthest object whose light could ever possibly reach us in the infinite future is currently about 62 billion light-years away. That's the ultimate boundary of our future observable universe. Compare that to the current boundary of 46 billion light-years. It means that, even if we wait forever, we will only ever see a factor of about 2.36 times more galaxies than we see today. The rest of the cosmos, beyond that 62 billion light-year horizon, is forever hidden from us. It is causally disconnected. We can never know anything about it by direct observation. This leads us to the final, humbling realization. The observable universe, this magnificent, 93 billion light-year wide sphere containing 2 trillion galaxies, is almost certainly just a tiny, tiny speck within a much, much larger whole. The entire universe, as opposed to the part we can see, could be infinite. Our best theories, like cosmic inflation, suggest that if the universe underwent that period of hyperexpansion in its first moments, then the entire universe must be at least 10 to the power of 23 times larger than the observable part. Other estimates, based on statistical analysis of the CMB, suggest it is at least 250 times larger, or about 7 trillion light-years across. But in truth, we have no idea. It could be finite but unbounded, like the surface of a sphere. Or it could be truly infinite, stretching on forever. And that, my friend, is the answer to how big is the observable universe? It is 93 billion light-years across. It contains 2 trillion galaxies, a septillion stars, and 10 to power 80 atoms, arranged in a vast cosmic web, all born from quantum ripples in the first instant of time. It is defined by the finite speed of light and shaped by the relentless expansion of space. And it is almost unimaginably tiny compared to what might lie beyond. It's enough to make you feel small, isn't it? But I prefer to see it another way. In this vast, cold cosmos, on a pale blue dot orbiting an unremarkable star in the suburbs of a spiral galaxy, beings made of stardust have managed to figure all of this out. We have measured the universe, traced its history, and peered back to its very beginning. That connection, that we are the universe contemplating itself, is perhaps the most beautiful thing of all. Thank you so much for joining me on this epic journey today. If your mind is even half as blown as mine is, please let me know in the comments. And don't forget to like and subscribe if you haven't already. It truly helps this channel grow and reach more cosmic explorers. Wherever you are, whatever time it is, I hope you look up at the night sky with a new sense of wonder. For me, it's getting late here. So, to all of you watching, from every corner of our little planet, good night. Sleep well, dream of galaxies, and we'll see you next time.